Transistors are the invention which revolutionized the modern electronic industry. In early days, the function of a transistors were achieved by a vacuum tube, which was very big, power-consuming, and prone to damage. Nowadays, the processor of the machine you're using contains millions, if not billions, of transistors, which does the same thing. But why need a transistor in the first place? The need of a transistor arose when we first understood the need to control the signals we use to communicate. Like a simple nod means yes, or the bat signal is a way to let Batman know we need him. This is a very primitive way of communication. The light means we need help, and the dark means everything is alright. But one important thing to note here is that the signal sent by us is being controlled by us. During the era of electromechanical computing, relays were used. They used the same concept and had a metal arm to control the flow of electricity. Vacuum tubes used to do the same thing, and now transistors controls the flow of current. Flowing of the current and making it present and absent is the basic essence of sending electrical signals, which can be used by computers. How transistors are made. Transistors are made of an element called silicon. Silicon is found in sand and is also a semiconductor, which means it lets the flow of current in certain conditions and blocks it in others, making it ideal for transistors. If we look more closely in a silicon structure, we'll see that the silicon atoms have 4 electrons in its outer shell. These 4 electrons are in covalent bonds with other electrons of the other silicon atoms, forming the silicon structure. As all the outer electrons of the silicon is in covalent bonds, silicon does not conduct electricity in this state, as there are no free electrons to carry the current. If we want silicon to conduct electricity, we need to give it free electrons and take away some of the electrons, so there are spaces for the current electrons to flow through. For this reason, the concept of doping comes in handy. If we replace a silicon atom with a phosphorus or any atom which contains 5 electrons, which is in its outermost shell, we will have an extra electron that is free to roam around the silicon structure. This is called an n-type doping. N stands for the negative, as there are free electrons in the structure. On the other hand, if we replace a silicon atom with a boron or any atom which contains 3 electrons in its outermost shell, we will have what we call a hole, which is the absence of an electron. The hole is free to move along the structure, as other electrons from other silicon and other atoms are ready to fill up the hole, and the hole moves through the structure. The hole is also called a positive particle. This type of doping is called a p-type doping. The p stands for the positive. If we have a p-type and an n-type silicon together, something interesting happens in the boundary of these 2 silicon. In the n-type region, where there are free electrons have the natural tendency to move to the p-type region. The electrons on the n-type goes on to the p side to occupy the holes. But remember, the n-type silicon and the p-type silicon are neutral in their own ways. Although they have holes and free electrons, doesn't mean that they are charged structures. When the electrons move over to the p sides and the holes move over to the n side, the atoms becomes charged in both sides of the p and n. The new electrons on the holes of the p side does not travel any further towards the does not travel any further towards the p-type silicon because the electrons are attracted to the light positivity in the n-type boundary. The boundary becomes positively charged in the n-type side and the negatively charged in the p-type side. This creates a potential barrier, or also called as a depletion layer, which stops the flow of current if it is not in an oriented manner. Depending on the direction of the flow of current, the barrier changes. Suppose we apply an electric current where the positive side is connected to the n-type silicon and the negative side is connected to the p-type silicon. We know that the electricity flows from negative to positive. That is, electrons are released from the negative terminal and flows towards the positive terminal. The electrons from the negative terminal flows through the p-type silicon, occupying the holes, and they reach the boundary. As we have discussed, that the p-type boundary, p side of the boundary is negatively charged, so the electrons are repelled from the boundary. Thus the current does not flow and the potential barrier gets thickened. This is what we know as the reverse bias. Now, if we provide electricity where the positive terminal is connected to the p side silicon and the negative terminal is connected to the n-type silicon, the electrons of the n-type now has an energy to move across the boundary. As the boundary of the n-type is positively charged, the new negatively charged electron particles are coming, and it will have an attracting force and will be able to cross the boundary easily, thus having the flow of electricity. This is called a forward bias. For all those electrical engineers out there, this is the basic workings of a diode. So what does a diode have anything to do with transistors? Well, a transistor is made when two diodes are connected back to back. If you've noticed, the transistor has two potential barriers. So regardless of the direction of electricity, one barrier would allow the flow of electricity, that is, be in forward bias, and the other would be in reverse bias. So ultimately, there will be no flow of electricity. This is the transistor in its off state. Now, if we add an external power source as shown, it will form a forward biasing diode. The external power source is connected what we call the base of the transistor, and the base region is very narrow. There will be a lot more electrons which cross the first barrier due to the presence of power in the base. But how are the electrons crossing the reversed biased barrier? Now, if you remember that the reverse biased barrier was formed by a thin layer of electrons. These electrons are now being sucked by the base source, dissolving the layer, and thus electricity is able to flow through normally. This is the transistor in its off state. As you see, the base current controls the state of the transistor. It acts as a switch but have no moving parts. This easy and swift ability to control the flow of current revolutionized the electric communication in computers. Transistors are the basic components of all electronic devices. In the next couple of videos, we will see how to use transistors to make logic in the computers. But before that, we need to understand the language of the computers, the binary, which is the next video. See you then.